En nombre del subsecretario Leonardo Beltrán, en la Secretaría de Energía, en la Subsecretaría de Planeación y Transición Energética, les damos la bienvenida. Este es parte del ciclo de conferencias sobre el futuro de energía en México, donde hemos estado organizando una serie de pláticas, conferencias aquí en la UNAM, en el Poli, en diferentes universidades de México, en el CIDE, para traer a México a profesores del más alto nivel, reconocidos mundialmente como el profesor Hamdi Tchelepi, para compartir su conocimiento, su experiencia, para que ustedes tengan la oportunidad de escuchar de ellos lo que están haciendo en universidades como Stanford y sobre todo para inspirarlos a que piensen en estudiar en lugares del más alto nivel, que soliciten este tipo de universidades, que conozcan más y todos, para que todos aprendamos, ¿no? Entonces, sin más, bueno, mi nombre es Germán Tribucay Vasconcelos, yo estoy con el Fondo de Sustentabilidad Energética, que es un fondo sectorial con la CITSENER, precisamente enfocado a, entre otras cosas, empujar el capital humano en México, ¿no? En temas de energía. Entonces estamos viendo cómo podemos contribuir en esta labor, ¿no? de todos aprender más, tener los mejores científicos, ingenieros, profesionistas en México en estos temas. Entonces, antes de empezar, quiero pedirle a Jorge Hinojosa, el presidente de la Sociedad de Energía y Medio Ambiente aquí de la Facultad de Ingeniería, que diga unas palabras. Les agradezco a todos los que ayudaron en organizar este evento, especialmente a la UNAM y a todos los profesores aquí presentes, a la sociedad de alumnos y, bueno, el profesor Hamdi Tchelepi, welcome to Mexico. Jorge Hinojosa will say a few words and then we'll get started. Thank you very much. Muchas gracias a todos.
Muchas gracias, Germán. Una vez más, me gustaría agradecer a la Secretaría de Energía, al Fondo de Sustentabilidad Energética por traernos estas experiencias aquí a la Facultad de Ingeniería. Es la segunda conferencia que tenemos de este ciclo del futuro de la energía en México. La pasada fue en agosto sobre energía solar fotovoltaica y es un gusto que confíen en nosotros y que vuelvan a traernos a ponentes de primer nivel como el profesor Hamdi Tchelepi. Thank you so much for being here and sharing with us your experience. Y quisiera agradecer, no nada más yo soy de la Sociedad de Energía y Medio Ambiente, pero también quisiera agradecer a las demás sociedades de alumnos que nos apoyaron con la difusión de este evento, a la Sociedad de Alumnos de Ingeniería Petrolera, al capítulo estudiantil de la UNAM, de la Society of Petroleum Engineers, al capítulo estudiantil de la APG, muchos de ellos aquí presentes, y bueno, los invitamos a todos los que aún no formen parte de alguna de estas sociedades a que conozcan un poquito más, se informen y sean parte de estos eventos. Ustedes pueden ser parte de la organización, enterarse de primera mano y ayudar a traerle estas experiencias a sus compañeros estudiantes. Asimismo, también los invito a que revisen los folletos que están dando del Fondo de Sustentabilidad Energética. Además del boletín mensual que tienen, hay muchas oportunidades para que nosotros como estudiantes podamos acceder a becas o a incentivos para estudiar un programa de maestría o doctorado en las mejores universidades del mundo. Y bueno, finalmente los invito de nuevo a que conozcan nuestras páginas de Facebook. A quien les llegó la invitación al evento, ahí se encuentran el enlace a las diferentes sociedades que estamos aquí reunidas, SOEMAS, AIP, CPE, APG. Y bueno, esperamos que disfruten mucho la conferencia. Gracias por venir.
Gracias, Jorge. Gracias, Jorge. Una cosa más rapidísimo. La conferencia va a durar como 40 minutos, 45 minutos, pero después vamos a dejar suficiente tiempo para preguntas y respuestas. Entonces, por favor, los invito a que vayan pensando en sus preguntas, que no tengan ninguna preocupación, miedo de preguntar todo lo que quieran y aprovechar el tiempo que tenemos aquí con el profesor. Gracias otra vez. Andy, welcome. Welcome to Mexico.
Thank you. I'm delighted to be here. Can you hear me? Can you? Excellent. So if you can, just raise your hand in the back and I'll shout a little louder. It is a true pleasure to be here. Thank you, Herman. Thank you, Professor Herrera. Thank you, most importantly, to the young people who are here. I'm delighted you made it, and I'm trying in this 45-minute period to entice you to look a little more on computational science with favor, on reservoir simulation with interest, and if you are interested in pursuing graduate degrees in a place like Stanford, we should talk. So that's sort of the overall pitch that I have for you. And now we'll get into the details. So most importantly, the start is point in the right direction. The starting point is to acknowledge all the people that have contributed to the material that I will be presenting. Given the nature of the talk and my guessing game together with Herman and Professor Herrera and others on what the audience experience and background is, I put together a talk that is quite numerical and computational, but not so deep into any one thing that I might lose you or you might lose interest. So the idea is to keep it going more on the breadth of the challenge of numerical modeling associated with reservoir simulation. And I'll say a few words about what that means. Again, as a professor, you actually don't end up doing much. The students do all the work, and this is a reflection of many of my PhD students over the years and a couple of professor collaborators from ETH and now in PKU, Beijing, and the funders of my industrial affiliate program, SUPRI-B. So, reservoir simulation is ultimately a tool to make accurate, efficient quantification of the uncertainty associated with trying to understand how subsurface fluids way beneath the surface move and get transported as a function of space and time. So it is important to recognize that you need to do the modeling of these complex things like enhanced oil recovery processes, managing subsurface water resources, the management and the design of CO2 sequestration processes. You want to keep in mind that the more you understand about the system, the better the prediction gets. But in the end, the complexity of the problem still means that whatever you make predictions of is not completely certain. And that's because a lot of the information that we have is actually a sparse sampling of the problem. So if you think about what controls fluid flow and transport in porous media, it's really the physics at the pore scale. You're talking about sub-millimeter scale representation of how fluids compete in the pore space. And that physics is governed by things at that scale. We refer to these as the conservation laws written in the Navier-Stokes formalism. But the idea is to not make predictions that go all the way from these tiny scales to reservoir scales that are tens of kilometers in areal extent and possibly thousands of feet in thickness. The idea is to translate information where the physics takes place at a small scale and make sure that you honor all the available information that you have about the reservoir, about the porous medium. Things like core data on the centimeter scale, electronic log data by lowering tools in wells and measuring saturations and permeabilities. Those are on the foot to meter scale. Then you can have seismic data that have multi-meter resolution. You can have transient well test analysis that gives you information about the average conductivity in the neighborhood of a well. And the idea behind reservoir simulation is to understand the complexity of the scale representation and capture the physics sensitive to the fact that things vary over a very large span of scales. What makes life difficult is that you normally have a very, very sparse sampling of the actual field. because you only have concrete information at a few locations in a highly heterogeneous system. And the analogy I made in an earlier talk today at PEMEX was, if I were to draw a map of Mexico City based on my experience over the last 2 days, unfortunately, it wouldn't be an accurate representation of your beautiful city. It will be lecture halls and hotel rooms. So you want to be careful in extrapolating too much about the data that you measure, recognizing that life is a lot more complex. Cities have streets and buildings and museums and parks and residents. And knowing that may actually be important to making a prediction than being obsessed with knowing a single or 2 or 3 or 4 pieces of information as in well data. So you want to keep that in mind. You want to integrate physics knowledge with measurements to make a prediction about oil and gas, their flow behavior, recovery processes, sequestering CO2 safely, and so on and so forth. So the problem is daunting. We refer to these kinds of problems as multi-scale, as in a huge range of scales, multi-physics problems, because that really means that at any given scale of representation, you have to resort to different kinds of descriptions and constitutive laws. We said at the poor scale you do Navier-Stokes, but that's unwieldy. So when you go to the next scale, you do what we call a Darcy averaged representative elemental volume. And if you ascend further up in the scales, you have to figure out how to upscale these governing equations and relations, permeabilities, porosities, relative permeabilities, saturation evolution. All of that physical understanding has to be embedded in this complicated natural system so you can make plans and predictions. So, I'm a reservoir simulation person, and like most human beings, we think we're very important. But you recognize that the world is much more complicated than what you like, meaning that reservoir simulation is only one piece of a puzzle that should integrate information about stratigraphic modeling, seismic imaging, structural and stratigraphic information, well-logged data, gridding, upscaling, production data information, well planning and configuration, actual measurements of fluid phases, pressure, volume, temperature, enhanced oil recovery, EOS calculations, the physics of fluid flow, phase diagrams. All of that has to be integrated into the reservoir simulator. So the reservoir simulator is a tool. The quality of the predictions from this tool, which we will talk about in more detail, is a strong function of the quality of information you put into it. So if you're making predictions, it's okay to blame the simulator, but it's also okay to interrogate and question all of the data that goes into that tool. And I'm going to get into more of that detail. So what makes life difficult in reservoir simulation? The trend is a further growth in complexity. So as the easy oil has been recovered, we now need to resort to enhanced oil recovery processes. We need to understand infill drilling possibilities. We need to worry about contamination. We need to worry about subsurface CO2 sequestration. So the complexity is growing. The complexity of the geometry of the system continues to grow. The resolution, people want to get more and more detail. This is this multi-scale nature of the problem. The more you see something, the more you want to get more information about it. And if you descend in scale, the property values change, as in permeability. So you want to resolve to the maximum extent you can. That's where computational resources become part of the reservoir simulation problem. You also, as you complicate the enhanced oil recovery processes, that means that the physics the simulator needs to model is now getting more and more complex. You have multi-phase flow effects. You have multi-component transport. You have reactions. You have geomechanical interactions between the solid skeleton and the fluid flow. You need to couple these things in order to understand the geomechanical response of reservoirs. If you're doing thermal processes like steam flooding, or just to understand the importance of temperature gradients in your reservoir, you need a thermal model. So life is getting complicated, but that's a beautiful computational science problems, right? The more complicated the problem is, the more interesting it becomes from a computational perspective. So how do you approach these problems? First, you have to recognize that, as I showed in the cartoon before, the problem is multiscale in nature, but it's also multiscale not only in space, as in the permeability and the porosity changes significantly in space, but the actual evolution of the physics is a very, very strong function of time. So when we say some process in physics is nonlinear, usually that really means nonlinear in time evolution. So it's important to understand that the problem is multiscale both in space and in time. So the challenges continue because when you talk about nonlinear problems that have lots of physics, that means you cannot worry about only one piece of the puzzle independently of the other. You can't say, I'll do flow, then I'll do transport, and maybe I'll do reactions. You cannot do that in nonlinear problems. These things evolve and affect each other simultaneously, which really means you have to be understanding the nonlinear coupling likely everywhere in the physics of the problem, right? So, and then we go back to the sparse sampling problem. So now you know you have a really complicated problem. Somebody is asking me to come up with a map of Mexico City, and I only have two pieces of information, hotel rooms and lecture halls, and a couple of nice restaurants. But still, I need much more information about how things are laid out in nature, in physics, to make a prediction. And that's what makes the problem stochastic, meaning that how oil and flow in a particular reservoir is a truly deterministic process governed by the laws of physics. The fact that we don't have complete information about the reservoir means that while the process is deterministic, our understanding of it is incomplete, and that makes it uncertain, right? So this is what people in computational physics refer to as uncertainty quantification. You have a complicated problem, you have limited information. That means that whatever you make a prediction about will not be exactly deterministic, right? So this is stochasticity due to missing information. But then in reservoir simulation, you don't only worry about making future predictions. You actually want to make sure that as you're making future predictions of oil recovery, the details of an enhanced oil recovery process, the actual reservoir is actually now producing. You have wells, you have production data, you have pressure measurements, you have seismic inversion results, and now you need to reconcile the actual measurements you get with your conception of the original model. And so the process of calibrating the model and refining it, redefining it if you have to, based on the data, is what we refer to as inverse modeling, right? So if you're constantly asking yourself, so I've evolved the permeability based on this saturation, now you have to redo the cycle again, update the saturation based on the permeability, and so on and so forth. So you have to do consistent forward and inverse modeling in a stochastic setting, right? So on this list, I can see 50 PhDs, right? In my group and in many other groups on the planet, there's been tens of PhDs on this subject, right? But we only scratch the surface, right? It's not, I sometimes hear people say reservoir simulation is a mature technology. I don't think we're talking about the same thing. It's far from mature, it's wide open, and in your country, it's a great opportunity, right? So keep that in mind. Now, drilling all the way down to the engine, the actual simulator. So we build these tools that solve the physics on a computational grid. So the first thing you have to do is worry about how to turn a reservoir system, your conception of geometry and properties, into a discrete representation of that sample. We refer to that as gridding, discretizing, dividing the city into buildings, if you like, right? So the building blocks of the model are the grid, but when you design the computational platform, you need to be careful in the software design aspects of the problem. So if you are a computational physicist or a computer scientist or a software designer, this is a rich avenue of research because we have to design these computational platforms using object-oriented design, modular technologies, separation of concerns, flexible platforms that allow for growth. This becomes a daunting software challenge. So I come from Stanford, the home of Silicon Valley, and people think that computation is all about computers. But actually there is as much computational science that has nothing to do with Intel and Apple, as much as we like them. There is a lot more computational science taking place than building computers. And people solve problems like this, right? Other pieces of the puzzle for the tool. The tool has to allow you to be flexible in your grid. This is what we refer to as unstructured gridding, which really means that instead of insisting on dividing the world into little cubes, you should let the geometry of the system tell you what the grid should be like. Whether it's tetrahedral or triangles, you let the geometry and the fluid dynamics of the problem define that for you. So it's important to allow for an unstructured, parallel, and scalable framework. What I mean by that is the following. These problems, as I hope you agree with me, are kind of really difficult to solve because of this huge scale and complexity of the physics, which really means that your best friend out there is to recognize that the problem can be divided cooperatively, so you simultaneously work on solving the problem by using more and more processors, more and more compute resources. But you can't simply add an additional computer for an additional couple of $1,000s and expect to double your computational efficiency. You have to make sure that the underlying algorithm, the way you solve the problem, allows you to scale the simulator, the physics, with the compute platform, right? And that's what I mean by scalable. So some of the most interesting developments in reservoir simulation technologies have to do with this idea of, let's see, combining multiscale methods with nonlinear solvers. I don't know why it's, maybe it's saying move on. But I refuse to do that. No, it's, so multiscale methods and nonlinear evolution problems are some of the most interesting aspects of recent developments in reservoir simulation technology. And I'm going to touch on a few of these items just to kind of whet your appetite and see if you're interested. As Herman said, if you have any questions, just raise your hand or chime in, please. Good. So by unstructured, what do we mean? You let the grid be defined by the complex geometry of the reservoir and its properties. So the best thing to do is to use a graph-based representation and turn everything into nodes and edges and discretize the problem as such. So if you do a lot of graph theory, or if you've looked at graph theory, simulators are best made flexible by making the entire problem a graph-based representation of the discrete physics. So you can discretize the governing equations using graph theory, and you begin to see graphs everywhere if you're developing these kind of simulation tools for unstructured grids. So you want to be flexible in your gridding and discretization, and then the problem becomes you end up with a representation of your physics now using these discrete representation of nodes and edges, and you have to find ways to solve that efficiently. So, unstructured reservoir simulation is not today still commercial practice, unfortunately, in my opinion. So, what gets into the way of unstructured grid workflows is that first, you have to make sure that you have gridding capabilities of the geocellular model and the reservoir properties. But then you have to have a gridding and an upscaling framework for both the grid and the physics. You have now to discretize the equations we talked about, these conservation laws, and then you have to solve them. And along the way, you need to define these fine-scale permeability distributions, upscaled transmissibility distributions. Discretization, MPFA stands for multi-point flux approximations, and then solving them using graphs. This workflow is still the subject of intense research, both in academic places like my group, but many others, as well as industry. Because the industry sees a huge future in bridging the gap between the geocellular model and logically rectangular representations of the grid. So, in order to get a reservoir simulator that actually scales, as in, I add compute resources, I get additional efficiency in computation, or I'm able to solve larger problems. For that to happen, it doesn't occur by accident. As I said, you can't just sit and wait for NVIDIA to give you the next version of their GPUs or Intel to give you the next version of their mic architectures. You have to do a lot of work to make it fit on that architecture. That includes rethinking the governing partial differential equations, rethinking the discrete representation, rethinking the solution algorithm, this idea of building algorithms and software design, and architecting the whole framework so that it is computationally sound and allows you to be flexible as you change your objectives. New physics, new enhancer recovery processes, so on and so forth. So you need to tie all of these things together to get a reasonably scalable reservoir simulation engine. So, where have we made progress collectively as a computational geoscience community? Progress has been made in these so-called multiscale finite volume formulations and multiscale mixed finite element formulations to describe the spatial variation of the properties and the evolution of the physics, the saturation distribution, pressure distribution, and so on. However, on the time side of the evolution, it actually has not been that progressive, meaning that we really have not paid close attention to the nonlinearities associated with the time evolution of our physics. And I'm going to touch on that in the next few minutes. So much more on spatial variation and honoring scalability as a function of spatial complexity, but much less progress collectively in the geoscience community on resolving nonlinear evolution in time. So I will cover a couple of things just to give you a sense of the areas we've been working on in my group. I'll do a time check because professors can talk. 20 minutes left. Perfect. Okay, so some summaries. Things that are very promising at the linear solver level, meaning that if you assume that the kernel of most interest is to solve the pressure distribution in your reservoir, that's actually usually a pretty good assumption, then there are very interesting developments that have taken place over the last few years, including the multi-stage preconditioning. CPR stands for constrained pressure residual. So the idea is to break the problem into multiple smaller pieces and to tackle it one at a time and then stitch the solution back together. Something akin to domain decomposition, but at the physics level. So we refer to that as multi-stage preconditioning. There is also a great deal of work. A couple of my PhD students many years ago worked on this idea of reorganizing the governing equation using what is referred to as potential ordering, where you actually rearrange how the equations talk to each other based on history of the pressure distribution in the domain. Then there is the powerful framework of algebraic multigrid. I'll show you a couple of pictures of how well it does in solving linear systems. So this is an area of huge progress, AMG, and this is a very popular acronym. And more recently are these algebraic multiscale formulations, AMS, which attempt to duplicate what multigrid does for linear problems, on elliptic linear problems, attempt to duplicate that to obtain even better scaling with problem size. And I'll show you an example of that. So, what are we looking at? The details are not as important as the big picture here. So I'm plotting. This is what people do when you're solving a system. You plot the residual, which is a sense of how far off from the answer you are. So think of a residual of 0 to be the answer you're looking for. And you're starting with an error normalized to unity. Think of that way. So I have an error of the problem initially at unity, and I would like to reduce it as I work on solving it. What parallel algebraic multigrid does is the following. For this problem, which is a million-cell SPE10 problem, SPE is the Society of Petroleum Engineers. 10 is the 10th comparative problem. So this makes life easier. So instead of every time defining your own problem, you say, hold on, I'm solving the 10th problem. This is it. So we're solving the pressure equation of the SPE10 problem as a function of additional processors. And if you have a scalable algorithm, it is critically important that this convergence behavior of your algorithm stays largely insensitive to adding more resources. This is referred to as strong scaling. So the convergence rate does deteriorate when you add resources, but it doesn't deteriorate too much. This is the mark of a reasonably scalable algorithm that you can work further to perfect its behavior after a 3 order of magnitude reduction. If you compare parallel algebraic multigrid to a standard something like incomplete LU factorizations with some degree of fill, those would deteriorate quite significantly as you add more and more processors, unless you do something special, such as a multi-level hierarchy or a multi-grid algorithm. So it's important to look at properties like this to see that the algorithm scales reasonably well as you add compute resources to the same size problem. Another kind of scaling which is critically important as you add more fidelity, more resolution to your reservoir description, you also don't want to suffer from slower computations. Meaning, so I have a problem of size 1, and I double it, and I double my compute resources. Ideally, if everything works nicely, the computational cost as in elapsed time should be the same. So I doubled my problem and I doubled my resources. But more often than not, what happens with non-scalable algorithms is as the problem size grows, the elapsed time, even though you're matching the resources, continues to increase. And that's usually because the amount of work it takes to solve a problem depends non-linearly on the problem size. So if the time is proportional to x squared, if x goes from 1 to 10, my elapsed time goes from 1 to 100, right? So I made my problem 10 times larger, but it's going to cost me even 10 times more, even if I add 10 processors to it. So it's important in scalable algorithms to make sure that you scale properly both ways. You scale if the problem is fixed and you're happy with its resolution. As you add resources, your convergence rate should not suffer, which should mean that as you add resources, you solve the problem faster. And then this kind of scaling, often referred to in computer science communities as weak scaling, where you really want, as you add resources and you add resolution, you want to stay put in terms of elapsed time. It's critically important to have both. And that's why designing a scalable simulator should be sensitive to all of these interactions to end up with something that is reasonably scalable. Another aspect of solving problems in a reservoir simulator is how things change in time. So a lot of reservoir engineers get surprised. They say, well, my simulator was behaving very nicely until, I don't know what happened. Time step came down and it's not converging. And the result of that is that the simulator can become extremely non-robust. It becomes too dependent on the details of the physics. And the details of the physics does change. When you have your reservoir and you deplete it, the physics is different from when you inject water, from when you're injecting water and alternating it with gas, from when you're injecting CO2 for enhanced oil recovery. So as the physics changes in time, you would like your simulator to be weakly sensitive to the change in the physics. So here, every line is a plot of a different linear system that your simulator sees as a function of time. And yes, it appears this system is easy to solve. The decline is quite steep. This system is much harder to solve. But you go from something like 4 iterations to something like 16 iterations. That is not necessarily ideal, but it's better than going from 4 to 4,000 or going from 4 to non-convergence. And that can happen unless you're sensitive to the change of the physics as time evolves for the problem. So a word about this algebraic multiscale solver. This is another way to scale the problem that is not a true multigrid method. It's actually a multiscale methodology. And let me go through the broad definitions of what that really means. So the idea is to break the problem into 2 stages. So you have a given resolution of the problem. You impose a coarser resolution. That's the coarse stage. And that's intended to actually take care of the low-frequency error modes. The local stage, which is an interpolation of the basis functions at small scale, takes care of the high-frequency error modes. So you can think of algebraic multiscale as a 2-level multigrid method with a special basis function that connects the coarse scale with the fine scale. And so just like with any other multigrid method, it lives and dies by the quality of its prolongation and restriction and the ability to represent the behavior across the error spectrum of frequencies. So another aspect of this algebraic multiscale framework is it can, and we have used it in connection with finite element methods. It's actually much more robust as a linear solver than a finite volume method. But we use it in a finite volume framework when we are integrating the nonlinear conservation laws. So you can see that in reservoir simulation, we're pretty agnostic. We don't care what numerical method you use as long as you solve our problem of interest. So in this particular case, we're combining a finite element multiscale construction with a finite volume multiscale construction to solve the overall problem. So that's the STAMS algorithm. So here is a plot of some pictures on the mic architecture. So a 20-core Intel mic architecture. I'm not going to spend too much time on the details. Just, I want you to look at the fact that we have different size problems. So these are, each result here is the ensemble, is the result of averaging over 5 different heterogeneous problems, just to make sure we're not skewed by one particular sample. So the average of 5, and you're looking at time versus the number of cores. So you take the same problem, in this case, you give it to 1 core, and this is the division between the setup stage, all the work you do to set up the core space, the prolongation, the restriction, and the solve stage, which basically iterates across the system between coarse and fine to solve the problem. So you can see, without getting into the details, that as you refine the problem, geostatistically, as you go from 2 million to 128 million, the scaling behaviors are actually quite similar. But in the end, absolute time is actually important for human beings. So it's important, and we get asked this question all the time, what does it really take? How long does it take me to solve a 128 million cell problem? And the answer, approximately, given what we know today with the algebraic multiscale framework on a mic architecture, you can think of, 50, 60 seconds, a minute, 1 minute to solve a 128 million cell problem. I may not look that old to you, but I would have given half of my life to solve a 128 million cell problem, not 1 minute. That was only 10 years ago. So this is a clear example where unless you combine your knowledge of the physics and high-end computational algorithms and software design. So the young man who does this has been working on the software development of algebraic multiscale for 5 years, right? So PhDs don't come cheap, but you see something quite interesting, right? So we are making progress in solving very highly detailed, very complex problems using basically something you can put on your desktop. A mic-based box still expensive, can fit underneath this table. This is something you would have needed an auditorium probably much larger than this, again, just 10 years ago. So computational science is really a fundamental enabler of these technologies. And I want to go back again to this idea that reservoir simulation is some kind of a mature technology. I don't think so. And this is only the beginning, right? So this is solving one linear problem on a many-core machine. There are still all of the things we talked about. Nonlinear, multiphysics, multiscale, stochastic, complex, optimization, uncertainty quantification, forward and inverse modeling. I mean, the list is long, right? So don't let anybody tell you, it's a done deal, right? It's not. Okay. So in 8 minutes, I'm told, I'm going to give you a quick overview of nonlinear solvers. And I'm going to actually skip a lot of this detail and show you an interesting representation of nonlinear dynamics. So I'll skip that. Let's use some pictures. So in multi-phase flow systems, just like, as I'm sure most of you have taken a basic numerical analysis class or a Newton-Raphson method, right? So reservoir simulation, as sophisticated as it may sound, ultimately boils down to wrapping everything within a Newton-Raphson iteration. And as we all know, even for one function R as a function of one scalar variable S, if the function has an inflection point, watch out, right? So it's not rocket science. I'm sure you guys have seen this before. I start with a guess. The root I'm looking for is the thing that makes R 0, which is this guy. So I start with an initial guess, S in it. I take a tangent. That takes me to this point. I take another guess, and I am literally oscillating around the inflection point, right? So unless somebody interferes with this process, this is a non-convergent process. The reservoir simulation problem with nonlinear analysis is, fortunately or unfortunately, like this times a million, right? So the dimensional space you're solving the problem, if you have 1 million cells, is 1 million coupled equations. So you don't want to go in each and every little equation and do this little fix. You need something a little more robust and a little more rigorous in terms of analysis to guide you. So I'll skip all of this beautiful mathematical detail, and I will show you here is a very simple, supposedly simple, 2-cell problem. Now, we're going from 1 function to 2, and I'm looking for the solution that would satisfy my equations as a function of the saturation in cell 1 and the saturation in cell 2. So this is now, luckily, still a 2-dimensional problem. So I have S1, these are saturations, volume fraction, 0, nothing, 1, fully saturated with that fluid. So S1 goes from 0 to 1. S2 goes from 0 to 1. In this case, I know what the solution is. It's this guy, because I did it by construction. And what you are looking at, these black lines, are the lines that a Newton method would follow if you take itsy-bitsy steps along this path. So Newton, in this case, if you take tiny steps, which is extremely expensive, is still guaranteed to converge. If you take standard Newton, actually you are guaranteed to diverge because there are all kinds of inflection points in the system. There are kinks depending on where you start in the system. So unless you start in the neighborhood of the solution, the chances of convergence are pretty small. But what one can do is follow the solution path as a function of how it evolves nonlinearly in time. Meaning, if you look at blind Newton tries to solve this complicated nonlinear system by actually guessing and iterating. But a better strategy, if you have some insight into the physics, is to actually evolve as a function of time by, instead of guessing and trying to converge this system, you actually evolve this coupled linearized system by using enough information about how the physics of multi-phase flow evolves in time. So you can do a continuation along the solution path. So here is another cartoon that sums up what this idea of continuation Newton does. So I have my time step from 0 to whatever time you want. Think of this as time. I have my unknown state variables. In this case, it's 1, but you can think of it, it can be 10 million. This is the solution path, which I remind you, we don't actually know. We're trying to get to this answer. And continuation Newton is based on the idea of combining the following steps. Taking tangents, which is a standard Newton step, but correcting it with the right step size. That's a sign that I should be done. But correcting that with a scale time step selector that is sensitive to the nonlinear time evolution in the problem. And if you do that, you can actually avoid going into la-la land where you cannot converge anymore and bring it back with a continuation step. And then continue until you get to the answer. So as long as you are within this bounded region defined a priori by the Newton-Kantarovich theorem, then you're okay. As long as you're within this boundary, you're okay. What you don't want to do is you don't want to fall outside either of these areas. And continuation is a way of keeping you reasonably on track towards your target. My last slide, I promise. There are so many, but I can't resist. So you can put all of this into the bottom line. What's the bottom line? Reservoir engineers want to solve more complicated problems faster. So the argument here is if you take itsy-bitsy time steps, the details of the problem are not as important. This is, again, our favorite SPE10 problem. This is half of it. This is all of it, right? So let's take a look, for example, at this. If you take tiny problems, this is the Newton iterations, the number of iterations you have to do. Ultimately, the time you spend in solving the problem is a function of how many Newtons you do. But if you take tiny steps, you really don't need such a sophisticated method because Newton, with small time steps, will converge. So the number of iterations goes from 660 to 470. That's okay. You go to a delta t of 1. Now you want to be aggressive and you want to take larger time steps. Suddenly, the difference between doing Newton versus what we call a trust region or a continuation Newton, you go from 3,000 to around 100, right? If you take an even more aggressive time step, now there is no competition. So Newton takes, say, 5,000. Trust region takes less than 100. What does that translate in runtime? You go from taking something like 100,000 seconds to, say, 5,000 seconds. So you are 20 times faster solving the same problem by using a trust region strategy. So if people tell you, why do I have to worry about the mathematics of nonlinear modeling? There's your answer, right? The guy next to you will run it 10, 20 times faster, right? So it's important to combine linear analysis, nonlinear solvers, time evolution solvers, in order to advance the scalable aspects of the reservoir simulator so we can solve our big problems. And I will stop here. Thank you. Yes. So as a reminder, and we will send you a lot more information, if you're interested in applying for or getting more information about our graduate program and the opportunities and the re-emphasis on the fact that simulation and CO2 sequestration are beautiful problems, ping me, and let's talk. The other thing I would say If you get admitted, you don't have to worry about the financing. So if you get admitted into our system, we will take care of you, right? We're simply looking for the best young talent to come north, right? For a while. Cheers.
Thank you very much, Profesor. ¿Escucharon eso? Si los aceptan en un posgrado en Stanford, no se tienen que preocupar por el dinero. Eso se puede financiar. Con ayuda de la universidad, con ayuda de la Secretaría de Energía, con CONACYT. Lo difícil es entrar. ¿Sí? Entonces, preocúpense por estudiar bien inglés, tener muy buen GRE, el examen de admisión, sus cartas de recomendación, y el dinero no va a ser problema para eso si entran a estas escuelas. ¿Okay? Buena suerte. Ahora, preguntas, por favor. Hay un micrófono aquí. Identifíquense, por favor, con su nombre y qué están estudiando para que el profesor tenga una idea de en qué grado están y pregunten todo lo que quieran, por favor. Gracias.
So, there will be questions? Or? Yeah, excellent.
I was going to say that I want to have more names.
Sure.
Their names,
yes,
their
yes.
names here.
Yes.
Hello, Eduardo Tello, Computer Science, Master's in Computer Science. Have you used the approach of using genetic algorithms instead of linear modeling to approach solutions?
We have not, but a lot of the people who look at the optimization problem, which is this idea of looking for, say, the optimum configuration of well placements, they use genetic algorithms to guide the solution in this search space for the optimum. So there is a lot of work at Stanford, not in my group, but in the Smart Fields Consortium. I can send you some information, Professor Durlovsky and Professor Aziz, where they focus on how do you compute optimum solutions to combine, say, well placement, well type, as a function of net present value and so on and so forth. So they use generic algorithms. They also use stochastic search algorithms. They use adjoint-based gradient algorithms. So much of the optimization activities are not covered in my talk, but I can connect you to a lot of people who do that.
Thank you very much.
Questions? So it's all clear.
Well, this was a very interesting talk. There are many topics to talk about. Have you implemented all these kind of methods in some software that you can share or something like that? Or how do you manage all this kind of software that's complicated?
So that's an excellent question. So the answer is it's a mix of tools and solvers. So we have our own in-house reservoir simulator, which we call GPRS, General Purpose Research Simulator, and we implement a lot of methods in it. However, all the stuff on multiscale formulations and nonlinear solvers are not in this simulator. So how do we manage that? It's kind of a long-term process. So I have, for example, the student who wrote the algebraic multiscale linear solver is going to graduate soon. He's negotiating for 6 months, so I think I'm going to let that happen. But then someone will have to come take that over and integrate it into our simulator. And this could be yet another 2 to 3 year project. On the multiscale framework, we have prototypes of the different pieces. And I still don't have the courage to say we will integrate it into the general simulator, because I think we still need a lot of additional algorithmic pieces before we do that. So it's really At any one moment in time, you will find that some of our capabilities are well integrated, but many of our developments are still in the pipeline. And this is also another argument for being careful with object-oriented design and software, because smart people come up with new ideas all the time. I see it with my students. And you don't want to tell them, here is a Volkswagen, turn it into a Ferrari. So you want to always be building for that Ferrari. Maybe it currently has a Volkswagen engine, but you don't want to build a VW and insist 5 years later to turn it into a Ferrari. And for that, you need software design. So I have 3 of the people in my group are software scientists. And I know that concept doesn't appeal to many people. I think it's a beautiful idea, because if you want to keep growing your computational framework, you can't redesign everything from scratch every time. You have to evolve and refactor and professionally develop, and we fully endorse that view. That's my approach.
Nice.
Hi, Professor. Thanks again for your presentation. My question is not necessarily about what you just explained. It's rather on how is it applied on capture storage, capture and sequestration, and like what's your research in that area?
Actually, we do, I would say, a third of my research group. I have a group of about 25 people between students and postdoc. About a third of them are working on exactly the CO2 sequestration problem, specifically focusing on modeling the evolution of CO2 plumes in the post-injection period. You see, in reservoir simulation, even though many people say enhanced oil recovery and CO2 sequestration are the same problem, actually, they are governed, subject to certain assumptions, they are governed by the same governing equations. However, in reservoir simulation, you benefit from something we refer to as convection-dominated displacements. This is when you're injecting stuff from an injector and producing stuff from a producer. In CO2 sequestration, the most interesting part of the physics happens after you stop injecting. So you took your power plant, you injected your CO2, and now it's into the subsurface. You close the valve after 10 years of injection, and you say, done. Not really, because the plume is going to migrate under buoyancy and dispersion. And interestingly enough, standard reservoir simulators neither understand buoyancy, nor do they understand dispersion. So if you want to build a simulator for CO2 sequestration, you can't ask a standard simulator to solve it for you, especially in the post-injection period. And in the post-injection period, you're going to have to defend what the fate of the CO2 is going to be, not after you stop injecting, which is probably 10, 20 years, but hundreds of years later, you want to say the CO2 isn't going to pop up somewhere in Mexico City, right? And so you need that long-term predictive monitoring tool. And it's a beautiful engineering problem, and it's doable, right? So modeling for CO2 sequestration is a huge part of our effort, and we will continue to focus on that.
I have a question, Professor.
Yes.
Can you say a few words in terms of the profile of students that you're looking for in your group, and to the top research topics that what is hot in research in your area today, and where do you see it going?
I will
Thank
do.
you.
So let me see if I can. If I said, I think I had something called challenges. If I can find it quickly, otherwise. Okay. So the profile of the student. a smart, young, physicist, mathematician, computational scientist, someone who is interested in combining math, physics, and numerics. So people say, well, I don't have a petroleum engineering background. So I plead guilty. All of my degrees are in petroleum engineering. But I have to tell you, I don't think any of my PhD students have degrees in petroleum engineering. They're almost always coming from mechanics, applied mathematics, applied mechanics, geomechanics, physics, computational physics, computer science, right? So that's the profile I want. But you have to be interested, right? So if you do physics and you do math and you do numerics, let me know. It's not only me. Many of my colleagues would be just as interested. And your GREs better be close to perfect. That's the profile. The research topics. So as I said, I think in every part of this problem, whether it's multiscale formulations for space, for time, nonlinear solvers, continuation Newton methods, uncertainty quantification, forward and inverse modeling, stochastic modeling using partial differential equations, each and every one of these topics is several PhDs. So there is no shortage of interesting computational problems to work on.
Hello, my name is Eric. Maybe a very basic question. Are some of the blue points recommended pathways of research? Or maybe you have some...
I don't think I got the question. Can you repeat that?
Maybe you can recommend that the blue lines are for starting research, or maybe you have some tips.
Oh, why blue
where
color?
to start?
So blue was intended to say, those are the two topics that I will touch on. That doesn't mean I'm not as interested, perhaps even more interested in uncertainty quantification and integration of that into forward and inverse modeling. I just didn't have enough time, as you saw, in actually covering two topics. But if you're interested in the details, I am happy to talk to you until you're bored about uncertainty quantification. So this is not intended to mean a differentiation between this versus that. They're all interesting. Seems everybody's tired, yes.
¿Alguna última pregunta o ya están? ¿Una más? ¿No? ¿Alguna pregunta? No. Thanks again. Wonderful talk.
Thank you. Thank you.